Hello all, I welcome you all to the 20th lecture in this course E614. In the previous lectures, we have dealt with PN junction diodes, metal semiconductor junctions, and BJT. So now we will step into metal oxide semiconductor transistors. But before we go there, let us discuss a very simple case of metal insulator semiconductor capacitors. So it is metal insulator semiconductor. So the most common structure of this particular stack is a metal layer deposited on top of a thermally grown oxide, basically silicon dioxide. This is some metal, and we have a bulk silicon. So the silicon can be N type, P type, whatever have you, and then it is contacted at the back by a metal with an ohmic contact. So as we saw before, ohmic contact just means that the contact resistance is much smaller than other resistances in the system. So we will deal today only with an ideal metal insulator semiconductor junction, and what we mean by ideal is we have no interface states. Why is this important? This means that there are no electric charges at either silicon dioxide interface or silicon dioxide metal interface, so that all the charges are either at the metal or at the silicon side. Second, no carriers or charges move across the interface, across the insulator at DC conditions. So when I apply a DC bias, I do not have any exchange of carriers from metal to the semiconductor or semiconductor to the metal for that particular matter. Under these simplified assumptions, let's just see what happens to the band structure of this stack. We have seen this many times. So we have a vacuum level, we have a metal with a particular work function Q psi m, and we have an insulator with a very large band gap or a small affinity. And I'm going to make a very simplified assumption in the sense that the Fermi levels of, or the work function of the metal and the semiconductor is the same, psi s. So this means that Q psi m equal to Q psi s. It's an assumption, right? What happens if this is not the case is that you will always have a band bending to begin with. We will deal with that later on. Okay, under these situations you see that there will not be any sort of a band bending, right? So I have my conduction band here, I have the intrinsic level, and I will have the valence band here, right? And I'm going to define this separation between the conduction band and the Fermi level to be psi n, and the separation of the Fermi level from the intrinsic guy to be psi b. Okay, not this psi, sorry, as psi b n type. Okay, so now the same thing if I write the metal semiconductor difference, which will turn out to be psi m minus psi s plus energy gap by 2q minus psi bm, right, which will turn out to be psi m minus psi s plus psi m. The same thing you can write if I have a p-type semiconductor. This is for n. Metal semiconductor work function difference for a p-type semiconductor will turn out to be psi m minus psi s plus Eg by 2q plus psi bp, right? Or I can also write it as psi s plus Eg minus psi p, right? So this is a situation when I have it at equilibrium, right? So now let us consider the situation where I apply a potential. For this particular example, I'm going to take a metal p-type semiconductor interface, right? And I have the vacuum level. I have, let us take that this is the original intrinsic Fermi level, and I have applied a negative potential on the metal. If I apply a negative potential on the metal metal Fermi level will increase, right? Or its actual work function will reduce. This is QV, and this is Q psi m minus QV, right? And I have the semiconductor, I mean the insulator gap, and there is a small slope across the insulator. Why? Because there exists a potential, right? And because it's a metal insulator semiconductor junction and it is not connected externally to any circuit, there is not going to be any current irrespective of the potential that I have applied, right? And hence the Fermi level will remain flat irrespective of the potential that I apply. But because of the fact that this potential will create a field, if I apply a negative potential here, it's easy to understand that I'm going to attract more and more holes into the in the semiconductor, and I use a p-type semiconductor, so I have plenty of holes, right? So what happens, the hole concentration at the interface is going to change. For that, the valence band should bend close to the interface, correct? Now if the valence band bends, and we have seen this numerous times, all the other things should bend. Right, so this is EF, this is EI. So the EI has also bent, and at x is equal to infinity, so this is along the x direction. At x is equal to infinity, or very far away from the interface, nothing is going to change a whole lot, right? So EI is still going to be flat, and at interface at infinity, I'm going to call it as EI naught, right? And at any point here, there is going to be some change very close to the interface, and this is EI of x, right? And you can see that if I apply a negative potential, EI of x is going to be higher than EI naught, right? Because it is going to bend upwards, and because it is bending upwards, I'm going to accumulate holes here at the interface, and the electrons are going to be pushed out. And it is this accumulation of holes at the interface is going to screen the electric field such that the entire metal is not depleted of electrons. I'm just giving you this feel of why this negative potential in the metal is going to attract positive charges at the interface, right? So now that we have positive charges at the interface, let us calculate what is the effective density of carriers in the semiconductor at any point. So we know certain relations. So we know that the density of holes can be written as NV e power minus EF minus EV by KT. And at any points, right? So at any point in the semiconductor, the intrinsic hole concentration in p-type is Ni, sorry. Oh no. EI minus EV by KT. So here I'm going to define a particular variable called psi p, which is a function of x, is the actual deviation of the intrinsic energy level from the infinity value. So it is this separation is what is written as q psi s, right? So it is this separation at any point is actually written as q psi s, right? And it's easy to see that if I substitute one on top of the other, I can get p any point is pp naught e power minus beta psi p, where beta is q by kt, which is called as inverse temperature, and np of x is given by np naught e power beta psi p. So basically there are two things which needs to be accounted for here, right? So one is the actual separation of the Fermi level from the intrinsic level, so which is what we call as psi b p, and the actual separation or the separation of the intrinsic energy level from the infinity values, which is q psi s. So these are the two things that we will compare later on. I just bring to your notice here because this psi bp tells you the actual density of carriers. So basically this is ef. So this is psi bp, right? And sorry, this is not psi bp, but it's a measure of psi bp. Psi bp is a measure of holes in the p-type semiconductor, and soon we will see that this psi s is a measure of electrons in the p-type semiconductor, and there is a correlation between the both of them. But then let's just continue, right? So with these expressions, now let us calculate the electric field at the metal insulator semiconductor junction. So how do we calculate the electric field? As we have done in PN junction, we will solve the Poissons equation. To solve the Poissons equation, let's write d square psi p dx square is a function of x is basically minus rho of x by epsilon naught, epsilon s actually, right? You're in semiconductor, and rho is written as q nd plus minus na minus plus pp minus np. pp is the hole density in p and the electron density in p, and these are the dopant concentrations, right? Ionized dopant concentration. And we know that at x equal to infinity, basically the total carrier density or charge density will turn out to be 0, which means that nd plus minus na minus turns out to be minus of pp naught minus np naught. So pp naught and np naught are actually electron hole concentrations at x tending to infinity, right? That's far away from the interface. So if I substitute that here, then rho will turn out to be q pp naught e power minus p psi p minus 1 minus np naught e power beta psi p minus 1. So basically what this tells is what is the change in the hole and electron carrier density over and above the ideal carrier densities, right? So ideal carrier densities are the carrier densities of electron hole very far away from the interface, and this, so your actual excess charge density or the charge density which causes field and the potential in the interface is caused by changes in the majority and minority concentrations away from the intrinsic numbers, right? So now let's substitute this back into this equation, and we will get d square psi s of x epsilon e power minus beta psi p minus 1 np naught e power beta psi p minus 1, right? Now how do I find the potentials? I integrate it, of course, and when I integrate it, I have to integrate it from 0 to infinity, right, on both sides. Now into infinity, of course, this integral will be a problem, right? To simplify this, what has been done is you multiply both sides by d psi of x by dx. So if I do that, I will get d psi of x by dx multiplied by d psi of s by dx. On the right hand side becomes much more simplified, minus q by epsilon naught pp naught e power minus beta psi p minus 1 minus np naught e power beta psi p minus 1 d psi of s, right? And at x is equal to 0, this is psi of p. At x is equal to 0, you have psi p of x is equal to 0, and x is equal to infinity, psi p will be 0, right? Because psi p, as we discussed before, is the deviation from the intrinsic level, which will be 0 at infinity. Now on the left hand side, d psi by dx is basically e, right? And at x is equal to 0, you have e is e of x equal to 0, and x is equal to infinity, electric field is obviously 0, and I have d, right? So basically I have substituted e to be d psi p of dx, and I'm going to make another substitution here such that psi p of x is equal to 0, and I'm going to take it as psi s, surface potential. Similarly, e of x is equal to 0, I'm going to take as es. Now both of them I can change the order of the integral. Es ede will turn on the right hand side will turn out to be 2 kt by q square q p n naught beta by 2 epsilon s. Then I have a bigger term, I'll write it down, e power minus beta psi p plus beta psi p minus 1 plus np naught by pn naught e power beta psi p minus beta psi p minus 1. The left hand side of this is obviously es square, and if I take the root of the right hand side, I will get the expression to be plus or minus root 2 kt by q ld. Ld is the diffusion length, and we know this is root kt epsilon s by pp naught q square. This multiplied by a factor which is very essential for our treatment henceforth. This determines the electric field and the charge at the surface, and this is something which will be used again and again in a MOSFET, in MOSFET, in many of the things that we will see in this course and elsewhere as well. So basically we have derived the electric field at the surface here due to an applied. So basically, what is the electric field here at the interface is what we have calculated. With the electric field, you can easily calculate the charge at the surface, which by Gauss law will give you minus epsilon s into E, right? Because E is the field emanating from the closed volume. So if I substitute, I will get Qs to be minus epsilon, plus or minus root 2 epsilon s kt by q ld, some function of beta psi s np naught by pp naught, and this f is basically this guy in the square root. Okay, now this term, this function f, plays an important role in determining the interface charge. So I'm going to plot this interface charge Qs as a function of the surface potential psi s, right? And there are different regions. So let's say I'll take it to be 0. First of all, let us take regime 1. If the potential V on the metal turns out to be negative, and we saw that if V is negative, EI of X will go above EI because the valence band is going to bend towards the Fermi level, right? And hence psi s is going to be negative from this particular equation, and hence psi s here is going to be negative for negative potentials. If psi s is negative, you can see that this function, the first term of this function, this one, will dominate, right? Because psi s being negative, e power minus beta psi s will be a positive and a large number, and this will dominate all the terms. The second term is a small value because np naught by pp naught, that is the electron concentration by the hole concentration, will be a very small number, so the second term will not contribute. So if V is negative, psi s is negative, so therefore your Q is proportional to e power q psi s by 2 kt. 2 comes out because of the fact that it's in the root, right? So your actual charge goes exponentially with psi s as at negative values, right? Now second regime, if V is positive and such that the psi s, that is the surface potential arising from this is smaller than psi b. Remember psi bp, right? So remember psi bp is the actual separation between the Fermi level and the intrinsic level, right? The intrinsic level is the so the intrinsic level tells you the intrinsic electron hole density, and the Fermi level below the intrinsic level tells you how much hole doped the p-type semiconductor is. So EF minus EI is proportional to the hole density, that is pp naught, right? So basically here and psi s is the deviation of the intrinsic level from the surface and to the bulk, right? So all we are trying to say is the charge density at the surface smaller, charge in the surface is smaller than the doping or majority carrier density in the substrate, right? So this is charge density at surface, and this is proportional to the majority carrier density in the semiconductor, right? It's understandable, right? So if, when this condition is true, you can go back to this expression and then you can see that psi s is positive, right? And this term is once again small because np naught is still smaller than pp naught, and you can see that the only term which now dominates is beta psi s, which is the second term here. So your actual q will be proportional to root of psi s, and hence so here you will have a square root dependence of charge with the surface potential, right, till some point. This is, let's say, psi b, right? And if I keep increasing this such that I reach a point where psi s is approximately equal to 2 psi b, in the sense that I have my band bending here. So this is psi s, right? So I have this band bending about twice the separation of the Fermi level from the intrinsic level. So in the sense that the bands have bent so much that I have a really large concentration of electrons in a p-type semiconductor, right? So under this situation, you can see that when I compare, when I come here, so basically I have very large electron concentration in a p-type semiconductor, and hence the second then So basically it is this term which will dominate, and hence here again the first term here will dominate, right? So basically under these situations Q will be proportional again to e power Q psi s by 2 kt. Once again